Innovation and Design Thinking. IDT-VTU. Module 3. Design Thinking in IT. Case Study. Scenario-based prototyping for designing complex software systems with multiple users. By J. Babu. Towards next-generation design thinking. Scenario-based prototyping for designing complex software systems with multiple users. This is a research work carried out by Gregor Gabrisiak, Holger Gies, and Andreas Sabel, System Analysis and Modeling Group, Hasso-Plattner Institute for IT Systems Engineering at the University of Potsdam, Germany. Design thinking is at its best if tangible prototypes can be used to capture and validate end-user needs and envision new products and services. However, today such tangible prototypes are not feasible in a cost-effective manner for complex software systems with multiple users and their complex behavior. To overcome this problem, authors developed a scenario-based prototyping approach for complex multi-user software systems that uses executable software engineering models including structural as well as behavioral aspects. Design thinking projects typically aim at single-user systems, such as a physical product or a piece of software, in which case often the graphical user interface and its interaction with the end user is in the center of attention. Design thinking can be characterized by the intertwined set of activities shown in figure. The careful collection of information about the problem in the activities understand, observe, point of view provides the basis for envisioning and evaluating possible solutions in the ideate, prototype and test activities. The design thinking process is a highly interactive and incremental process driven by people with different backgrounds and experiences. This heterogeneity is important to capture as many viewpoints as possible during design, not only the ones of technical experts and engineers. Through these diverse backgrounds, prototypes are essential in establishing a common understanding between these different persons. If the aim of the design process is a physical product, prototypes can be made of paper, wood or some other physical material that is easy to work with. A wooden prototype of a cup holder, for example, serves as a model, since end users can use the wooden cup holder to observe behavior that is similar if not the same with the final product. Prototypes allow studying the aspects of the physical product that the design process is interested in. End users can grab the prototype, experience and judge it to propose ways to improve it. This works well because the prototypes are tangible. They are quite similar to the final product in the sense that they expose similar behavior and allow observations that are relevant to improve the design. When designing a graphical user interface, GUI, of a software system, the situation is somewhat different. The reason is that the final product is not as tangible as a physical product. Authors argue that the GUI is still the most tangible aspect of a software system, and that might be a reason why it is often in the center of design thinking processes related to software. However, a GUI is a rather individual and user-specific view onto a software system. For multi-user software systems, GUI prototypes are not suitable for expressing the big picture or the insights and needs leading to the prototype's design. To make the user interface tangible and invite feedback from users already early during the process, paper prototypes are developed, so-called low-fidelity prototypes. These paper prototypes allow design thinkers to discuss with end users about the behavior of the final system. Once the user is satisfied with the low-fidelity prototype, a high-fidelity prototype is developed using flash technology. This prototype is a mock-up of the final product. Thus, it enables the discussion of more detailed UI issues. However, the same is today not possible for complex multi-user software systems and their behavior, which is not only dependent on how individual end users interacts with their respective GUI, but mainly on how they interact with each other. Finally, the design is completed and engineering takes over. With respect to modeling, a paper prototype of a graphical user interface serves as a model. The same is true for high-fidelity flash prototypes, which allow for even more detailed observations. In many engineering disciplines, simulation and prototypes are employed on a regular basis to better understand the problem at hand and identify innovative solutions. It has also been advocated that for complex problems and organizations, simulation and prototyping can help to recognize design conflicts early, can invite people to play innovative what-if games, and that the feedback from simulations of prototypes can in particular stimulate innovations. For software, the pioneer Fred Brooks also stated long ago that the hardest single part of building a software system is deciding what to build, and that often prototypes can be more articulate than people concerning the what. However, the wicked nature of complex software, respectively, the requirements have prevented us from realizing the full potential of prototyping and simulation for complex software, especially when dealing with multiple users. When multi-user systems are in the center of attention, many usage scenarios can be obtained during the design thinking process. These scenarios can be regarded as process instances. They need to be related to each other and analyzed. For instance, it is crucial to find inconsistencies between the scenarios or to validate them by stepping through the respective processes. Scenario and process modeling as well as simulation techniques are important concepts to study the relationships between usage scenarios. Additionally, scenarios are also a suitable representation for prototyping things you can't pick up. Information about artifacts involved in the process can be extracted from these scenarios as well. This means relate state modifications of artifacts to activities within the process, assign relevant documents to stages within a process, and even to deduct responsibilities between artifacts and end users. Another key problem for designing complex multi-user systems is traceability. The information collected by the different team members is usually not well captured and linked with the envisioned solutions in form of prototypes. Therefore, the evaluation of ideas is often restricted to the prototype alone and cannot be navigated back to the original source of the design decisions, such as interviews or background information. An evolutionary prototyping approach might help to avoid such information loss by documenting the feedback and the resulting modification of the used prototype for each step along the way. Losing this information is a limitation for an effective test of prototypes within the team or with end users. The consequences of losing information are even more dramatic when it comes to engineering the product envisioned by the design thinking team. When engineering takes over, the decisions that have led to the design are not readily available. The design process and the engineering process are somewhat decoupled through such handovers. This exposes a severe problem, since engineers might make engineering decisions that are not in line with design decisions. This is due to the fact that they are not aware of the rationale behind design decisions. Therefore, design and engineering must be better linked. This means that design artifacts that document the design process and its decisions need to be available during engineering. Research method. Author's research method is based on the design thinking process and guided by the research hypotheses presented in the next slides. This research starts by gathering insights about the problem domain, trying to understand how practitioners of the design thinking process use it for multi-user software systems and how virtual prototypes can improve this process. Afterwards, authors observe and interview practitioners from their project partner D-Labs GmbH to gain needs. The following synthesis leads to a point of view, then prototype the concept to evaluate the hypotheses, applying tests that are experiments. The prototype will then be modified according to the insights we gather during these test sessions in multiple iterations. Hypothesis 1. By introducing the idea of prototyping scenarios to create a common understanding and validate the scenario as well as the underlying assumptions, it is possible to get more reliable, namely commonly agreed upon results. During the validation of requirements and insights, end-user feedback is invaluable. However, confronting them with models in notations they have never seen before is futile. So, in order to improve the validation of insights, the quality of the feedback gathered during validation sessions needs to be increased. Consequently, authors formulated Hypothesis 2. Hypothesis 2. By being able to present a scenario-based prototype, it is possible to gather quality feedback, which end users would not provide using common validation techniques. Also, validation sessions are quite time-consuming and expensive to conduct. In order to help with this problem, authors want to evaluate Hypothesis 3. Hypothesis 3. One can derive tangible prototypes from software engineering models for complex multi-user software systems that are suitable for end users and all design thinkers in a cost-effective manner. Expected impact. By finding a suitable answer to the research question and the hypotheses, one of the most powerful tools from the design thinker's toolbox can be made available for developing complex multi-user software systems. While it is currently not feasible to completely validate insights in a cost-effective manner, authors hope to integrate an incremental, cost-effective prototyping approach in order to produce more reliable and better results not only during the validation and synthesis of insights, but throughout the whole lifespan of a design thinking project. Understand and observe. Author's project partner D-Labs is a startup company located in Potsdam, Germany. They provide expertise in design thinking for complex multi-user software products to customers as a service. Their projects are run based on a catalog of design methods. The portfolio they offer includes trainings in these methods. However, their main focus and expertise lies in running software design projects. D-Labs covers the requirements engineering stage of a project. To do so, they start by understanding the problem domain through a 360-degree view. Afterwards, they start end-user research through observations and interviews. See the figure. Figure shows the D-Labs process separated into its divergent and convergent phases. The succeeding synthesis phase, during which the point of view, POV, is created, iterated and refined, is the most important one, since the ideation of solution concepts relies on the correctness of these agreed upon findings. Based on the ideation, the prototyping stages usually start with paper prototypes, which are iterated till a prototype of the graphical user interface is created. In order to maximize the reuse capabilities of their results, apart from a detailed documentation of how they got there, D-Labs also provides reusable software engineering artifacts using example, Flash or the .NET Framework 3. The point of view is quite important for a design thinking project. It contains the most important needs and insights that have been gathered from end users about object of study. However, in multi-user processes, there are different end users or participants who have diverse, potentially opposed needs. In order to help design thinkers in this context, they need support to capture and validate and manage all of these needs and different roles to later on decide which ones to emphasize. See the figure. Figure shows that not only the design thinkers need to understand the gathered insights, but also the end users. Usually, there are only few validation sessions due to the high costs of traveling to the end users and validating insights or prototypes with them. This stresses the importance of the interviews and the validity of the insights gained from them. While it is always possible to talk to certain end users to correct minor mistakes, for example, different names were used for the same process artifacts, it is rarely feasible to gather all end users in order to establish a common understanding of the process. Point of view. While all tools and methods of design thinking can be used for complex multi-user software systems, some of them do not scale well for such a scenario. Therefore, they have to be adapted to fit the needs of this domain. For multi-user processes, this implies the necessity to validate insights and assumptions as cost-effectively as possible. Traditional validation techniques are too expensive to be used in multiple iterations, since these mostly rely on bringing multiple end users together to present them the current state in order to gather feedback on this state. Validation sessions also need to provide tangible artifacts of some kind in order to ease the end user's understanding. Otherwise, the end users are decoupled from the assumptions gathered from them or the ideas that are generated based on these assumptions. See the figure. Figure shows a validation session to validate insights and requirements. Feedback can be gathered by presenting and translating the current state for end users. The possibility of conducting validation sessions remotely helps to circumvent potential travel costs. An incremental approach, which provides means for validation sessions through multi-user sessions as well as single-user sessions, might also help to emphasize the validation of certain subsets of insights. Based on the insights authors gained from the research question and the resulting hypotheses, they came up with a concept for scenario-based prototyping for designing complex software systems with multiple users. This concept is shown in figure. In the beginning, as with all software projects, initial insights have to be elicited. 1. These initial assumptions can then be captured using formal requirements models. 2. Formal models offer helpful capabilities, such as being able to pinpoint inconsistencies automatically or to propagate modifications consistently. These models enable an interactive simulation of the captured insights with a domain-specific animation on top, which behaves like a real prototype, allowing the end users to experience how they were understood. 3. Thus, the end users interact with the prototype models, which are semi-automatically derived from the current state of the insights gathered by the design thinkers. During such a simulation session, all end-user interactions with the prototype simulation are recorded and incorporated into the prototype models. After multiple sessions, a software engineer needs to evaluate the recorded interactions. 4. To judge the end user's approval of the prototype model's current state. This also represents a measurement of how well the end users share a common understanding of the insights gathered by the design thinkers. If the approval is still not satisfactory, the insight models can also be adapted. 5. More or less automatically. Prototype. Authors explain the current state of the implementation of their concept based on the process as explained in the previous slide. The prototype was first presented in 4th International Workshop on Requirements Engineering Visualization, 2009, Rev 2009. As shown in the figure, it has been built on top of the Eclipse environment and a model-driven development platform developed in a group. Therefore, in relation to this effort, a concept to efficiently maintain traceability in a model-driven engineering domain have been developed. Other extensions of the employed platform provide more flexible means for developing simulators based on EMF models, simulators for interactions in distributed service-oriented systems, and some efforts for migrating some required features to the Eclipse platform. Initial elicitation. Traditionally, insights are initially elicited using interviews, which appear to be the most effective technique for a wide range of domains and situations. This is also the best practice used by D-Labs. For the prototype, however, the initial elicitation is out of focus. It is assumed that initial interviews were conducted and that the results are already available. Based on these interviews, design thinkers have to identify activities, a preliminary causal order of activities, abstract roles these activities are assigned to, and scenarios with interactions. These findings are synthesized into requirements models, which in author's domain are role-based business processes. See the figure. Figure shows an example of such a model, which is an initially synthesized process of ordering an article initiated by a role named publisher. Currently, the used insight models are based on a subset of BPMN elements enriched with additional semantics. Roles are an important concept in author's approach because they are an abstraction layer between individual end users and views on the prototype. Each role can be related to a different view that reflects the aspects that are important to the respective end users. For example, views may differ in their level of detail or whether information is hidden, visible, or even highlighted. Insights elicitation validation. It is important to validate insights incrementally since the elicitation is a highly subjective, creative, and dynamic process. This implies that insights, which are initially elicited, may be incomplete, inconsistent, or even incorrect. To overcome this issue, author's approach allows multiple end users, or an individual one, to reflect on existing insights. Furthermore, the approach supports finding new insight by conducting a simulation session based on prototype models, which have been automatically derived from the given models capturing the insights. In general, there is a conceptual overlap between these models. Nevertheless, prototype models have additional execution semantics. The derivation of prototype models is configurable. The configuration depends on the view of the role itself, and the level of detail that should be shown to the end user playing a role. The level of detail depends on the intention in terms of which domain-specific aspects should be validated. Example, whether activities in the prototype models are in causal sequential order or not ordered at all. The latter approach enables a less restrictive simulation and thus could help the elicitation of alternatives within the process. For example, in case of an employee view, only the context of the employee is visualized by using a generic workplace visualization. In this view, end users can interact with other roles or software systems by triggering domain-specific primitive actions, examples phone calls, visits, or emails. The simulation uses the role as a parameter to control which interactions are shown to or highlighted for the end user. Instead of creating a customized GUI for each project like in, the domain-specific views can be reused for different derived prototype models. Since conducting these validation sessions cost-effective is also an important aspect, providing them remotely by visualizing them in a web browser saves travel costs and simplifies sessions for multiple users. See the figure. Figure shows two screenshots of the interactive visualization. Left, shows the initial screen where one of the 4 available participating roles of the process can be chosen. These roles are as an admin, as a publisher, as a reviewer, and as an author. Right side of the figure shows a screen during a simulation session of an end user playing the author role. In this figure, the author prepares an email for the reviewer including a document, which has to be reviewed. Currently, this tool supports only one view during the simulation. While this view is appropriate for end users who directly participate in the business process that is elicited, other views have to be integrated to include other groups of stakeholders as well. For example, the potential maintainers of such a complex multi-user software system. When an end user triggers one of these domain-specific primitive actions, it may lead to new activities and interactions, which have to be considered as new insights that were not elicited before. Roles that are not played by a stakeholder during a simulation session are automatically simulated. Simulated roles do not only react on interactions, but also initiate interactions with other roles and therefore other stakeholders. Initially, simulated roles do only interact with generic patterns coming from the prototype models. It means a stakeholder who plays the reviewer role receives an email from the simulated author role with the content review article. The authenticity of a simulation session increases over time. For example, as soon as an end user plays the role author, the exact wording of this email is saved and might be reused in further simulation sessions. Thus, interacting with simulated roles feels as if the interaction takes place with another player. This feature plays into the prototype models and, furthermore, can be more or less automatically incorporated into the insight models. Evaluation of sessions. Based on recorded interactions, which emerged during simulation sessions, a domain expert can evaluate the session and the findings gathered. Each action during each simulation is recorded and mapped back directly onto elements of the underlying insight models. The interactions of stakeholders that are recorded during simulation sessions can be analyzed quantitatively and qualitatively. Quantitatively, it can be examined, like how many stakeholders actually used a specific communication primitive to finish a specific activity as shown on the figure. See the figure. Figure shows quantitative visualization of multiple simulation sessions of the role author. More importantly, it is possible to verify the identified process by observing the path that stakeholders agreed upon throughout the simulation sessions. Based on these results, changes to the insight models can be approved or discarded. Qualitatively, it is possible to see which recorded interactions diverged from the identified path through the considered process, thereby revealing conflicts or alternatives within the process, which might have been ignored otherwise. Tests and learnings. To evaluate our hypotheses, authors established an experiment design which can prove or falsify the assumptions. Experiment design. During the last months of the first project year, authors conducted a pilot study on the feasibility of their approach, comparing their results to validation sessions merely based on a BPMN model representation and a method expert explaining it to an end user. Within this pilot study, authors elicited 2 partially complex, multi-user processes from 3 university assistants and validated these processes 8 weeks later. This delay was chosen to ensure that the validation results were based mainly on the everyday experiences of participating in these processes instead of memories from the interview during the elicitation session. Experiment results. During the evaluation sessions, authors made different observations that led to many insights. First of all, apart from usability issues of the prototype, author's approach is feasible. Feasible in a way that allows us to generate interactive simulations for end users, enabling them to experience how they were understood. The process that is replayed for and with different end users allows them to experience the content of a model that would require a bidirectional translation by a modeling expert otherwise. Bidirectionally is mandatory to ensure that gathered feedback can be used to modify the model. During the validation sessions, authors enforced the active enactment of tasks within the interactive visualization, which is much less abstract than talking about how to do these tasks. The explanatory sessions produced feedback with additional comments on already captured activities, while the usage of the prototype led the assistants to enact refined tasks and comment on priori unknown decisions within the already captured tasks. This is an indication of the barriers that modeling notations pose, even when explained. The graphical distance between two notation elements within a model is relatively small and usually does not represent the mismatch of semantic information or abstraction levels that they might convey. The explanatory sessions had no means of synchronization between the presented model and the flow of comments that were gathered. The assistants started uniformly by pointing on the initial activity in the model and moving their finger along as they commented on the process. However, two of them stopped at certain activities, looked up to the ceiling and proceeded further through the process without moving their finger accordingly. This is a strong indication for a missing synchronization between what they told to the authors and the current state of the process that they were walking through mentally. When using the interactive simulation, the end users are always in a well-defined state of execution of the process. Hence, their direct input can always be mapped to these states. Authors also noticed that end users were not willing to comment within the tool, but rather prefer to talk directly to other persons in the same room. Therefore, authors have to adjust the experiment to include remote telephone sessions to test how one can either promote the usage of textual input into the prototype as well or to capture and automatically synchronize an audio stream to the output of our interactive simulator. Not surprisingly, the willingness to use of the simulator was not consistent throughout each session. Depending on whether or not all tasks can be achieved within the interactive visualization, the motivation declined or stayed the same. Discussion of results. Main issue is authors have to deal with a fidelity problem. Although the focus lies on providing a prototype to experience a multi-user process prototype, the usability of the prototype must suffice for end users playing through a simulation to have all the degrees of freedom they need. Thus, confronting them with an unstable or incomplete version of the prototype leads to two problems: they cannot see the underlying process to validate it, and they rather comment on the implementation than on the model. Thus, all experiments were rather explorative in nature and yield no empirically significant results. Still, the feedback during these sessions indicate that authors are on the right track. Summary and future work. Authors could conceptualize how end users can be involved more directly in the validation of insights. Their concept relies on the simulation of formal models with an interactive suitable, it means domain-specific visualization on top. Allowing end users to directly provide feedback about the model during such a simulation can be used iteratively to evolve the underlying model till all end users share a common understanding on the validated model. This concept has been realized in a prototypical implementation that authors used to conduct initial experiments. These qualitative explorative experiments emphasize the feasibility of this approach. Authors also received feedback which indicates that their approach is suitable for eliciting requirements which are likely to be overlooked otherwise. Authors were able to generate tangible prototypes semi-automatically based on formal models. Authors still need to empirically evaluate them. Thanks for watching. Comment for any suggestions. Like, share and subscribe for more videos.